Hello everyone, I'm Bai Liu from MIT. It's my great honor to introduce our work, Optimal Control for Networks with Unobservable Malicious Nodes. I will introduce the background, model, algorithm, analysis, and simulation by sequence. First is the background. The motivation behind the topic is twofold. First, modern networks are becoming increasingly complex. The network dynamics may be non-stationary and non-stochastic, and some nodes may be unobservable and uncontrollable. Second, modern networks suffer more and more from attacks like the DDoS attack or SQL injection attack. So in these cyber attacks, the hijacked nodes may be also unobservable and uncontrollable, and the dynamics can be malicious. To tackle these issues, we aim to develop a control algorithm for networks that the external arrival process is malicious, and some nodes execute malicious policies, and their states are unobservable. Note that our definition of malicious actually allows the adversary to dynamically change the attack policy based on our actions so that they can maximize the damage. Then we introduce the model. We consider a multi-hop network with n nodes. The nodes are classified into two types, accessible nodes and malicious nodes. At the beginning of each time slot, the nodes receive external arrival. This external arrival process can be malicious. And then the accessible nodes takes action to control the network, which is also the controller's policy. And then, meanwhile, the malicious nodes also have their own actions, but these actions are controlled by the adversary and is unobservable to us. Here we define the network event sequence to be the actions taken by the adversary from the beginning to the end of the time horizon. We then introduce maliciousness matrix to characterize the behavior of the malicious nodes. So a network event sequence is said to satisfy a constraint if there exists a policy such that some specific conditions are satisfied when the adversary implements the network event sequence. So for instance, in 1996, the W constraint was proposed. It said the condition was that for each interval of length W, there exists a policy such that under this policy, the net increase of queue backlog was not positive. And then in 2018, the VT constraint was proposed, requiring that there exists a policy such that under this policy, the peak queue backlog was no greater than VT. And now we propose the Qt constraint in this paper. We only require the final queue backlog to be no greater than Qt. We further define that a network is said to have W or VT or Qt constraint dynamics if all network event sequences it can generate are W or VT or Qt constraint, respectively. We now use a toy example to illustrate the maliciousness matrix. So suppose there was a node which receives one packet every time slot and plans to transmit two packets to the destination. The time horizon was divided into 10 intervals. During each interval, for the first half time slot of the interval, there are two extra malicious arrivals, while for the rest of the interval, there was no malicious arrivals. We can show that the network is W constrained with W equals to T over 10. And it is VT constrained with VT equals to T over 20. And because all the packets are cleared at the end, is Qt constrained with Qt equals to 0. We now summarize the difference between the maliciousness matrix. So we can see that the double constraint actually requires the dynamics to have some periodic patterns. It is possible that a network does not have double constraints. The VT constraints limits the burstiness of the network, and the QT constraint is the most relaxed one. Actually, we can rigorously show that Qt was no greater than Vt, and Vt was upper bounded by W times some constant coefficient. Here we also have some conclusions. We can show that our algorithm can stabilize all stabilizable networks in previous works, those works with W or Vt constraints, and for some networks that are not guaranteed to be stable on the previous algorithms, they might be stabilized by our algorithm. So basically, our algorithm was stronger than previous algorithms. Then we introduced the core idea behind our algorithm was to construct an imaginary network where every node is observable and controllable. So for instance, for the network in this figure, node 2 and node 3 are malicious. And the corresponding imaginary network, we assume that these two nodes are observable and controllable, and we color them in pink. Of course, it is possible that the queue backlogs and the actions in the imaginary network might be different from the real network, so we denote them by X and G respectively. The intuition of why this method works is that the imaginary network now becomes easier to stabilize because it's fully observable and controllable. Therefore, if we can also stabilize the gap at the same time, then the real system is stabilized. We apply a Lyapunov optimization framework. We define a Lyapunov function which is the sum of the squares of the accessible queues, the imaginary malicious queues, and the gaps. If we can stabilize these three terms at the same time, then the real queue backlog also gets stabilized. We aim to minimize the one-slot drift. However, the yt here is actually unobservable to us because it requires the knowledge of the malicious queue backlogs. So we assume that we can actually estimate the malicious queue backlogs. Of course, to make the algorithm practical, we only assume that we can make the estimation sparsely. So basically when we make an estimation, we update the y. Note that we allow the estimates to be erroneous here. So basically the yt can be actually different from the real yt. Otherwise, we just simply use the most recently updated yt. Our algorithm was named MWUN, max weight for networks with unobservable malicious nodes. So at the beginning of each time slot, if we need to make an estimation, then we make it. Otherwise, we just skip this step. And then we solve this optimization problem. And then we apply the accessible policy F to accessible nodes in the real network. And then we apply both F and G to all nodes in the imaginary network. We first show the stability results. We show that for a Qt constraint network, if Qt were sublinear in time horizon t, And the average delay in estimation is also sublinear in time horizon t, and the estimation error at time t was sublinear to t, then the network is rate stable under our algorithm. Based on this theorem, it is straightforward to show that the stability region of a given network is the set of network event sequences with Qt being sublinear in time horizon t. We can also show that our algorithm is throughput optimal. We then analyze the robustness of our algorithm to estimation errors. We first define that a state-based algorithm with those algorithms that determine control actions solely based on Q information. Our algorithm, max weight, back pressure, and traditional reinforcement learning methods in network are all state-based. And then we show that for a Qt-constrained network where Qt was sublinear in time horizon t, but the estimation error was at least linear to t, then there does not exist a state-based algorithm to achieve rate stability. Meanwhile, we show that our algorithm can stabilize the network as long as the estimation error was sublinear in t. Therefore, we can say that our algorithm was maximally robust. Finally, we consider a network with 12 nodes. 8 nodes are accessible and 4 nodes are malicious. So the adversary tends to allocate data to heavily loaded nodes because these nodes are easier to be destabilized. So the malicious injection has a quantity of 2. It can inject into node 1 or 4 or 10. It selects the node with the largest queue. And for malicious node 2, for the first half of the time slot, it transmits 5 packets to node 3. While for the second half of the time slot, it only transmits 1 packet to node 3. Node 3 always tries to transmit 5 packets to node 7. And malicious nodes 4 and 6 apply the join the longest queue policy, which is in contrast to the JSQ policy and should be a very bad policy. Here are the numerical results of our algorithm when there were no estimation errors. The top left figure shows that the traditional Maxwell algorithm cannot stabilize our network. If we take a closer look into their stabilizing policies, we can see that they all perform pretty well. Of course, when the average delay in the estimate grows larger, the performance may downgrade a little bit. The bottom left figure shows that the gap between the real queue backlog and the virtual queue backlog is under control. And finally, the bottom right figure shows that our algorithm captures the change of the malicious behavior pretty well. So in the middle point of the time horizon, there's a change of the behavior of malicious node 2. Node 2 decreases its service rate from 5 to 1 sharply. From this figure, we can see that our algorithm captures this change pretty well. We decreases our transmission rate from node 1 to node 2 so that the queue backlog at node 2 won't get accumulated up. We finally show the results on our algorithm when there were estimation errors. As we can see, as long as the estimation error was sublinear in t, our algorithm still reaches rate stability. Thank you, and all questions are welcome.